We're going to look at the Bohr model of the atom today and tomorrow. Next week we will look at the quantum mechanical model of the atom, and then by Tuesday we'll move on and start looking at nuclear physics, specifically alpha, beta, and gamma radiation. So we're going to be using the law of conservation of energy to describe what's going on here. Whatever is going on to produce those wavelengths in hydrogen or those wavelengths in neon or whatever, it has to do with energy being conserved. That's what this is all about. And we're going to do our best to describe the Bohr model of the atom. So very quick review because I've already done so. Rutherford model of the atom.
Can I get the unit handout?
Certainly, Nick. Were you here when I gave you the first part of it, which was just a few sheets? So I've already explained this. I'm not going to spend an inordinate amount of time on it. Rutherford's model of the atom predicts that atoms should continually be producing electromagnetic radiation because the electrons are accelerating. Atoms do not continually produce EMR, so Rutherford's model is wrong. Rutherford's model can't explain how a proton in hydrogen and the orbiting electron in hydrogen produce those wavelengths. And why not other wavelengths? Why not all wavelengths? Why wavelengths at all? It can't explain what's going on. So we've already talked about this. We've seen it. Here are the 4 lines. So if you had a black and white handout, you would be looking at the top diagram, and those are the wavelengths. And I see some of you are looking. So from my vantage point, I can see the 4th line in this middle image. This middle image is, I believe, the same one that I copied and pasted into your document and I printed. I can see it. It's right here. But now that I'm looking at this, I don't think this is the image. I think it's dimmer on yours, isn't it? But can you accept the fact that it's there, just for the time being? How many of you can see it on your handout? It's almost, speaking of optical illusions, it's almost like, yeah, it's there, and then you go, wait a minute, am I actually seeing something, or is it not there? In reality, what we were looking at yesterday is the bottom image. Anytime there's any ambient light, any extra light bouncing around, you're never going to see total darkness in between the lines. And that will allow you the opportunity, hopefully, it's like a great white elk. Once in your lifetime, you might see this color. It's very, very dim in hydrogen. So this is what you were looking at probably yesterday. And I would suggest that's why when I said green, you were not seeing green. It's because the green is being covered up by some blue. And I don't know if any of you remember, but when you looked through, did you see a green line or was it basically blue? Probably blue. Did anybody see green? Not something you'd characterize as green. So this is the spectrum. This is called the emission spectrum for hydrogen gas. Believe it or not, these are the actual colors. They're not the relative brightnesses, but if you isolate those wavelengths in a perfectly darkened room, those are the pure colors. If you look up the wavelengths that I've just given you here, these are the colors. Now, I have to admit something. These are the colors that I'm getting when I do searches for wavelengths on my computer and I put it up here. The quality of this projector may change something. I don't know, right? I mean, you cannot imitate perfectly real life with a computer screen. Here we go. This is our data, and some years I do it with an n equals 2 as well, but I was watching the clock yesterday and we didn't have enough time. So when we do these calculations, the first thing you need to do is determine the angle by taking x over L and going inverse tangent. This is nothing new. This should be really obvious to you. I've already taken and calculated my x's up here because I think we measured from side to side, didn't we? So you have to divide that by 2. Anyway, when I do that and then use lambda equals d sine theta over n, because even just remembering back, Christian was holding the diffraction grating here, ish. We had lines drawn on the board like over here. There's no way that the angle between my arm and that is less than 10 degrees. So that's why we had to do that. These are the wavelengths I get. Anybody else get those same wavelengths? Pretty much. Okay, let's do a percent error. Let's do the 718 minus 656 divided by 656 and then times 100. So you're taking the experimental value of 718 minus 656, you're hitting equals, you're dividing by you're dividing by 656 then multiplying by 100. Right? You're doing this, 718 minus 656 over 656 times 100. I think you're getting 9%-ish. What is it, Alex? 9.45%. Now, I've said, particularly in Physics 20, if you can do a high school physics lab and get within 10%, you're doing a good job. It's nothing to be ashamed of. That being said, I was a little disappointed because we're normally closer, and I chalked that up to me not measuring L properly. You could certainly do the percentage errors for the other ones. I don't remember what you'll get, but I know they're less even than 9%. I think you're getting around 5%, but it doesn't matter. We're getting in the right neighborhood. You're not getting ultraviolet radiation or infrared radiation. You're getting in the right neighborhood. Okay. So the Bohr model of the atom is going to explain these wavelengths. Niels Bohr was a fellow who came up with some pretty wild ideas as to why this is happening. And we can't get into the real reasons why he developed these formulas. And I don't mean to be dismissive, but the math is too complicated. I probably wouldn't even remember half the math from when I learned this in university. But this is the key idea. His theories are going to explain why hydrogen emits particular wavelengths when excited and absorbs particular wavelengths when not excited. He's going to explain why those 4 wavelengths of visible light are emitted by hot gas but absorbed by the cool gas. Now, his theories are also able to explain the spectra of other atoms. If you look at the periodic table up here, I don't have a laser to point at this, so I'll just point with my finger. Lithium, sodium, potassium, rubidium, cesium, francium, all of those elements in group 1A, Bohr's model of the atom can come up with explanations for the spectra. And all of those atoms, if you're in a chemistry class, you know this, they contain 1 valence electron. And basically what Bohr does is he treats the entire atom except for that electron as 1 charge, and then he treats the electron as the second charge, and he's able to come up with formulas that work. There he is. I'm told that this is in his university days, so he's probably early 20s on the left and then on the right. So there's some of his math. Do you want to start learning it? Well, I'm going to have to learn it again first because I don't remember. That looks like somebody's having a psychotic episode and writing stuff on the board, right? It doesn't look real almost. 3 basic ideas present. And if you understand these 3 ideas, everybody, you'll really say it's one big picture. Okay, it's one big picture. And again, we can't get into the whys. It's a great discussion to have, but we don't have time for it, and it won't lead anywhere. So, electrons can orbit a nucleus only at certain distances. So we can imagine just for the time being that you have electrons in some kind of orbit. Maybe it's circular. There are only certain places where the electron is allowed to orbit. Okay? It can orbit at this distance, or this distance, or this distance. And what I'm telling you is that the orbits are quantized, which is a really bizarre thing. And it may not seem too bizarre to you until I tell you the electron is allowed to be in this orbit, or this orbit, or this orbit, but not in between. But then it gets weird when I tell you, but the electron can change orbits. Right? And if that doesn't bother you intellectually, if you think, yeah, that makes sense, then I don't think you're picking up what I'm saying. The electron can go from one orbit to another orbit, and it is never in between. Spatially, it's this far away from the nucleus, and then it's this far, but it is not in between at any point in time. It simply is here, then it's not, but it's here instead. It turns out, and I am only mentioning this not because the formula I'm giving you is needed by you, but it might help you understand something. First of all, you are expected to know that as you go out to further and further orbits, the distance increases like a parabola. So the first radius, let's call it 1. The second radius is 4 times bigger. The third radius is 9 times bigger than the first radius. So every time you go out a radius, you're going out a total distance that's the square of R1. But I want to stress this because it might pop up on an exam. See this formula at the top? You can use this formula for hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. But they all have different numbers here. What this number that I've highlighted is the radius of the first hydrogen orbit. And if I multiply that by 25, I'll get the radius of the fifth hydrogen orbit. But it's hydrogen. And lithium would have the same formula, but it would have a different number for R1. I mention that because I've seen on exams, diploma exams, they give you this formula. And you need to understand it's for hydrogen only, with that number. And if at any point you have a question, please let me know. So this is what we are saying the atom is like. We have all of these possible orbits, and now we're going to stop using the word orbit and call it energy level in physics. We are saying that the electron can be in the n equals 1 energy level, and I'm drawing the electron huge, aren't I? Because the nucleus of hydrogen is a single proton, and a proton is 1,800 times bigger, more massive than an electron. Okay? There's the electron in the n equals 1. Here is an electron in the n equals 2. The electron can go from here, in that orbit, to here. It's allowed to be here. It's allowed to be here. It's not allowed to be in between. Which means, and I'm going to actually start revealing more than I need to at this point in time. So I'm going to be saying stuff that I will reveal in your notes in a second. In order for the electron to go from here to here, it needs to gain energy. There's more energy here. But if it goes from here to here and is never in between, then that energy it gains has to be gained at once in a lump of energy. Sounds like a photon to me. Okay? But a photon whose energy does not exactly equal this jump can't be absorbed. If this electron here absorbing a particular photon puts it at this point in space, well, it can't. It can't be at that point in space, so it will never absorb the photon to begin with. Which is a strange kind of thing. It's like we're saying the electron knows whether it should take it or not based on where it would land. The electron in the atom could be in the n equals 3 or it could be in the n equals 4. That's all the first idea here. Let me go back and just highlight it. That's all this is saying. Electrons in atoms are quantized. Not just hydrogen, but all atoms. The total energy, this gets complicated mathematically. Do you agree that an orbiting satellite has a speed that depends on its distance from the Earth? Satellites at lower orbits tend to go faster. But then again, at lower orbits, they have less potential energy, don't they? The total mechanical energy, potential and kinetic, that a satellite has around Earth depends on where it is. Similarly, this electron that's in orbit has electrical potential energy and it has kinetic energy. And the total of those two energies depends on where it is. Mathematically, the relationship is complicated, but there's a dependence there. And what that means is since the location is quantized, the energy is quantized. So when I'm saying the electron can have this location or that location, I'm saying that the electron can have this amount of energy or that amount of energy. Both position of an electron in an atom, orbit, I guess you could call it, and the total energy of the electron in an atom are quantized. And each orbit corresponds to a particular energy. I think that's pretty obvious. If you go to a different orbit, that's a different location, so it's a different energy. Now, do you remember that Rutherford said the electrons are in orbit around atoms, but there's a problem with that because electrons in orbits are accelerating centripetally, but accelerating charges should generate EMR always, and accelerating electrons in atoms don't always do that. Here's how Bohr gets around that. He just says that's the way it is. That electrons are allowed to be in an orbit and never lose energy. You know what he's saying? There's an exception to Rutherford's principles of electromagnetism. There's something unique or special about electrons when they're in atoms. So these electrons that are in a particular orbit, or what we want to call energy levels, are allowed to stay at that distance from the nucleus and not lose energy. In other words, they don't radiate EMR. Rutherford's problem is they're supposed to radiate EMR. Bohr's solution is to say, you know what? They don't. Live with it. There's an exception to that rule. Since, according to Bohr, and it will change a little bit after the weekend in terms of what we learn, the size of the orbit and the shape of the orbit is constant in a particular location, we often call these places stationary states. We're not saying the electron is stationary, we're saying the energy it has is stationary. It's not losing energy. So, point 1 says location is quantized. What does that have to do with anything? It leads to point 2. Right now, if you understand point 2, I could care less about point 1. Point 2 says electrons are allowed to have a certain energy or a different energy or a different energy. In theory, an infinite number of different energies are allowed, but you can't have energies in between the ones that are allowed. I want to pause there and just let that sink in or see if anybody has any questions or comments about that. Okay. This, it turns out, when you use Bohr's theories to do some calculations, this is an energy level diagram for hydrogen. And I don't want you to worry about the numbers yet, okay? What I want you to notice, I don't like that thing there, I don't know why it's there. What I want you to notice is that the bottom energy state is called the ground state. And I have a handout I'm going to give to you in a second. The bottom energy level, which is called the first energy level, is called the ground state. Ignore the numbers right now, okay? They're not important. And I want you to notice that for hydrogen, the difference between the ground state and the next energy level is huge. I'm talking energy, okay? If you look at the distance between the first radius and the second, it's not huge, it's small. But the energy change between them is huge. So if I want to get an electron that's in the ground state up to here, I have to add a lot of energy to that atom. If an electron falls, quote, falls from the second down to the first energy levels, it will lose a lot of energy. But the energy level transitions in this region are generally speaking quite small. So the amount of energy involved from one level to the other is not a constant thing. Between 1 and 2 it's huge, and then between 2 and 3 it's less, and 3 and 4 is even less. It's got a nice unique pattern to it. So, the point that I've labeled number 3 puts a bow on this whole package. An electron is allowed to move from one energy level to another as long as energy is conserved. So if I have an electron that goes from this position to this position, that's a gain in energy. It has to gain that amount of energy. It cannot gain that plus a little bit because it's not allowed to be a little bit higher. It has to be in that precise location. It turns out, and there's an exception to this is almost always the case, that if an electron goes from one energy level to a higher energy level, so it gains energy, it does so by absorbing a photon. How much energy does the photon have to have? Exactly the difference between the two energy levels. Otherwise, the key doesn't fit the lock. If you have an electron in an atom, that goes from, say, the 5th energy level down to the 3rd energy level, then that electron has lost energy. And I want to pause for a second here. Am I going too fast? Are you following this? Okay, because it seems like I'm way ahead of schedule where I normally would be. Maybe I've just refined this.
I just had a question.
Of course.
Why does the distance increase between the ionization level and the second last, the 6th one? Why does the distance increase?
So, are you saying why doesn't this fit everything I've told you so far, this diagram we're looking at right now?
Yes.
Because it's not hydrogen. So, we can have a short discussion about this. And I think it's a valuable thing. I told you well, I didn't tell it to you this way, but I will tell you now. For hydrogen, lithium, sodium, potassium, rubidium, cesium, all those, francium, the physical distance from the center of the nucleus to the electron is governed by this formula. So if you put in R1 for hydrogen, and I have not forgotten what you're asking, I just want to demonstrate something to everybody that I think is important. This is the formula you would use to find the orbital radius of electrons in stationary states in hydrogen. So if I put the number 5 in, I will be finding, by taking 25 times that first radius, I will be finding the orbital radius. And all of those group 1A elements follow that rule, okay? On the other hand, and I don't want to get into the numbers too early, but it's been brought up, so it turns out that all of those elements in group 1A follow an energy law that looks like that. And I'm not going to put E1 in for hydrogen, but I'm going to tell you that this results in here, for physical distances, it results in the first orbit, the second orbit, the third orbit, the fourth orbit. The distances get bigger and bigger. But this results in terms of energy, big energy change, small energy change, smaller, smaller, etc. So we don't need to know that, but what we need to know is these patterns, whether we're talking physical distance or energy, these patterns are only true for group 1a atoms. So when we look at this, this is just some other atom. Bohr is not able to come up with any of the numbers for this energy level diagram, okay? But the principle is the same. Other people come up with models which can calculate these energies. Bohr is only able to do it with hydrogen. Have I answered your question?
Yes.
Okay. So, these are some energy levels within a hypothetical atom, which means it's just totally made up anyway. And when you look at true energy level diagrams, sometimes they're all over the place. Sometimes there's a pattern to them, sometimes they're not. It's complicated. If you have an electron which goes from the 5th down to the 3rd energy level, which, by the way, the diploma exam uses the word jumps a lot, even if the electron goes down. It will often say it jumps from the 5th to the 3rd energy level. Then a photon will be emitted. Okay? Are you with me on that? Why? Because the electron loses energy. Since the electron is part of the atom loses energy, and a photon comes out of the atom. And it's a mysterious thing. It's not like the atom has a little bag full of photons waiting for the electron to fall and then it spits one out. The photon is not there, and then it is. On the other hand, if you get an electron in an atom to jump to a higher level, then what's going to happen is it has to gain an amount of energy, and that amount of energy is because of the absorption of a photon. And whatever this change in energy is, that's the energy of the photon. Right, we're starting to get some math in here now. So, say, if I knew that energy at the top, and I knew the energy at the bottom, where the electron started and where the electron ended, if I subtracted those two energies, that has to be the energy of the photon involved in what's going on, whether it's emitted or absorbed. Similarly, if you knew this energy and this energy, then you could find the change in energy, which will be the energy of the photon. And again, exactly. Like if we take this one as an example, and I worry about being overly repetitive here, but I think it's an important idea. Let's say that this energy here, I'm going to put a number on it. Let's say that this energy is 120 nanometers. Is 3 electron volts of energy. What this means is that whatever number this is, energy-wise, and whatever number this is, the energy at the n equals 6 is 3 eV more than the energy at the n equals 2. This is not hydrogen. It's just some made-up atom. So that means an electron to go from 2 to 6 needs to take in 3 electron volts of energy. I'm saying it's a photon. What's the wavelength of that photon? Well, that's easy. That's 1242 divided by 3. Or if you don't want to go that route, we're using E equals hc over lambda. But can you work out for me what that wavelength is in nanometers? .414. 414 nanometers. Deep violet light. Violet photon. So that photon comes along, that, you say 414? That 414 nanometer photon comes along, bangs into the atom somehow, and then is gone, and the electron is no longer at the bottom, it's at the top. Do you get what I'm telling you happens? My question to you is, what do you think would happen if it were a 410 nanometer photon? Now, I admit you don't have numbers on the diagram to look at, but do you see that a 410 nanometer photon is more energy than 414? Smaller wavelength? Is it a lot more energy? No. If I add whatever this energy is to this, the electron probably is going to land here. But that's forbidden, which means that photon is not going to be absorbed. That photon goes right through. The one that is absorbed will be a dark line in the absorption spectrum. If I shine all of the wavelengths of light towards this atom with low energy states, it's going to swallow up some and the rest will just go through. And that's the dark line spectrum. Let's look at some questions. An electron in an atom drops to a lower energy level. I hope I've played my cards right here and set up the stage for this. An electron drops to a lower energy level. The initial energy level is 2.24 electron volts higher than the final energy level. What happens? So who can tell me something that happens? There's at least 3 or 4 things that we could write here.
The electron releases a photon.
The electron releases a photon, okay? I'm going to just tweak that a bit and say the atom releases a photon. And in fact, I don't think we even need to say atom or electron. I think it's just sufficient to say a photon is emitted. So there's photon emission. And I'm going to write photon emission because we would probably see the word emission here, everyone. We probably wouldn't see release. But they mean the same thing. But can we be more specific? Can we elevate our response here to a physics 30 level? And I think Sasha's going to have something to add here if I give her a minute.
The photon will have a wavelength of 554 nanometers.
How many?
554.
554. Is that rounded at all?
Yep.
Okay. So what Sasha has done is she said E equals hc over lambda, and she's used 2.24 for EV, and you get 554. Okay. So you could be even more specific and say a 554 nanometer photon is emitted. But hang on a second here. This never says anything about the photon. That doesn't say the photon has that much energy. Why does the photon have that much energy? That just says the electron's energy level that it started at was 2.24 eV higher than where it ended. Why does that become the energy of the photon? Do you know, Anna?
Because it's the energy released by the atom.
Yeah, it's the energy released by the atom. It's the energy lost by the electron in the atom. And we can sum that all up by saying because energy is conserved. And I want to actually write this down because it's a formula we're using here. We're saying the change in the energy of the electron is the energy of the photon. We're saying that if that's the energy lost by the atom or by the electron in the atom, then that's the energy that has to be accounted for at the end of the day. Has to be the energy of the photon. And these introductory questions are not exam questions. I'm just warming you up to the idea of what's going on here. An atom absorbs an 850 nanometer photon. What happens to the atom? Well, the atom gains energy, yes, but I want to know more specifically what happens to I guess, the structure of the atom. It changes subtly. Can you tell me in general, Craig, what happens?
The distance from the electron to the nucleus increases.
Right. So I'm just going to say the electron goes to a higher level in the atom. Wherever the electron in the atom was, the electron goes up to a higher level. Now, we can't say which level it arrives at, but we can say how many electron volts of energy it goes up by. Because just like the previous question, the energy lost was the energy of the photon. Here, the energy gained is the energy of a photon. So you can say an 850 nanometer photon is absorbed. But we can convert that to energy. Have you got it, Alex?
1.46 times 10 to the negative 9 eV.
That cannot be
Oh,
right.
I see what it is.
Electron volts are typically, 2, 3, 1, 4, maybe 10. Have you got it now?
1.46.
1.46 eV. So 1.46 eV is the energy involved. And you can say, well, here's a really important thing. Yes, the electron gains 1.46 eV, but what that tells us is that in this atom, there are two energy levels which are 1.46 eV apart. Okay? Because it had to start at an energy level and it had to finish at an energy level, so there must be two energy levels that are that distance apart. I use the word distance to mean energy there, that are that energy apart. A certain atom can emit a 120 nanometer photon. What does this tell us about the structure? Well, let's figure out the energy. And you'll notice here, I'm just assuming that, like that, you can figure out the energy of a 120 nanometer photon. It's 1242 divided by 120 if you want it in nanometers, if you want it in electron volts. Page?
10.35.
Sorry?
10.35.
10.35. So what that tells you is that there are two energy levels in this atom. We're not saying that an energy of an electron in a level is 10.35. We're saying that there are two energy levels that differ by 10.35. Okay, we looked through a diffraction grating yesterday at hydrogen. We saw 4 lines. Let's pretend we saw 4 lines, okay? We saw 3 lines. Trust me, there's a 4th. Why aren't there more lines? I'm going to tell you in a second that hydrogen has an infinite number of energy levels. Those 4 lines are caused by electrons falling from particular energy levels to particular energy levels. Why aren't there an infinite number of different lines? Alex?
There are only that many energy levels within the nanometer range for visible light.
Right. Of all of the differences between the energy levels, only 4 of them give visible light photons. You remember that big gap I said between n equals 1 and n equals 2? I'm going to tell you that anything that falls down to the ground state, that's going to be ultraviolet because that's a huge, huge amount of energy. There's a sweet spot in between somewhere where we get visible light photons. So I've chosen to answer this by saying, of all the different pairs of energy levels, only 4 have differences which correspond to visible light photons. I'm handing out an energy level diagram or a series of diagrams for hydrogen that we will need in another minute or so. And I'm having a hard time with this font. So here's a copy. I put it on your Google Classroom, and I'll see if I can tweak it to make it work. we're not using these right away, and don't worry about what they are. Don't get bogged down in the details of this handout. It's just for a couple of minutes from now. Bless you. And number 5, describe the electron transition that would occur in any atom that would result in the shortest possible wavelength. Anybody have an idea? And it's a little tough for you to answer because I haven't really said too much about energy level diagrams other than there are different levels. Do you have an idea, Cyrus?
There's going to be a big jump.
Right, it's got to be the biggest jump. And by the way, if we're going to emit, it's going to be a jump from a high level to a lower level. What this means is it has to be from the highest state down to the bottom state. Now, remember I told you the lowest state is the ground state? The highest state is called the ionization state. Because at the highest state, what we would do is say the electron is not even part of the atom anymore. Don't wrap your head around where that physically is in space. It doesn't work that way. So it would have to be from the ionization to the ground state. And earlier I said I thought I was a little ahead of schedule. I'm not. This is just perfect, okay? Because we still have a couple of things to talk about. Any questions with 5? How do the wavelengths and frequencies of the photons in those 2 diagrams compare? Like, the diagram on the left is a photon emitted. The diagram on the right is a photon absorbed. I'm asking you if you can tell me anything, without even knowing numbers on those energy levels, if you can tell me anything about the 2 photons compared to each other. Alex?
The one on the left has a longer wavelength.
Why does the one on the left, yes, have a longer wavelength?
Because there's less energy.
Right. This is a smaller change in energy, and a smaller energy of a photon is a longer wavelength. Or it has a smaller frequency. Whereas over here, the wavelength is smaller, but the frequency is larger. If we knew numbers on these levels, then we could actually calculate these wavelengths and frequencies. All right, let's turn the page, please. And we're going to do a few examples, and then you're going to have some problems to do. Use the energy level diagram for hydrogen that I have just handed out. And I want to just take a minute and speak with you about this diagram. I want you to notice that there's 2 sides, and I want you to go to the side where the bottom energy level is labeled as 0. So you're looking at the side of the energy level diagram, and I believe it will be the back side of this. Will it be the back or the front? I think it might be the back. So you scroll down, you see E1 equals 0, 0 electron volts is the ground state. And then if you look at E infinity, which is called the ionization state, it has a value of 13.6 eV. It is crucial that you know and remember and understand these numbers mean squat. What matters is the difference between 2 energy levels. So for example, take 5 and 4, take E5 and subtract E4. And I believe you're going to get 0.306. Okay. Now keep in mind, there are other decimals here. Turn to the other side of the sheet. And you'll notice at the bottom, E1 is negative 13.6. Okay, how can we say energy is negative? The answer is that some of this energy is potential. And we're allowed to say 0 is the location for potential energy wherever we want. I don't want to get too bogged down in this, but does this hole punch have gravitational potential energy? Yeah, because it's above the floor. Okay, it's on the floor. Does the hole punch have gravitational potential energy? Yeah, relative to the basement. Told you there was a basement with a pool table and a bar and all that stuff. Then there would be potential energy here relative to the basement. Sadly, there is not. There is a basement, but it's dusty. Nothing fun there. So we can assign the bottom negative 13.6. Look at E infinity now. It's 0. The difference is the same. Take E5 minus E4. Literally take negative 0.544 minus negative 0.85. You get the same number. It doesn't matter which side you use. I'm going to try to get us to use the negative sides. Okay? So, let's get at it. What is the wavelength of the photon emitted when an electron in hydrogen jumps or falls, whatever word you want to use, from the 7th to the 3rd level? Well, I have this nice energy level diagram, and Anna, I think this is what I'll maybe provide for you. It just doesn't have the right spacing. And the numbers might be slightly different, but you would always be given the diagram on an exam. So we want to focus our attention on 7 and 3. 7 and 3. To me, if I've done a decent job of this, you really shouldn't need to write anything down. You're going to subtract those two and say that's the energy of the photon. But I am going to write down here that it would be, this is basically what you're doing. And by the way, it's always upper minus lower. Don't go final minus initial, always upper minus lower. So negative 0.278 minus negative 1.511. A 1.2, a paltry 1.2 eV photon is emitted which is 1,007 nanometer photon, some infrared light. Are we okay with A? You write down what you need to write down. You'll see in a second why I don't think I want you to write down everything, because otherwise you would never get any work done. What is the minimum wavelength that can be emitted by hydrogen? Well, the minimum wavelength is the most energy. It must be from the ionization state down to the ground state, which no matter how you cut it, if you look at one side of your sheet, it's going to be 0 minus negative 13.6, which will give you negative 13.6. If you look at the other side, it will be 13.6 minus 0. Bottom line is it's a 13.6 EV photon (91 nanometers), ultraviolet. And we're done. I have one more example here, and this is only for people who have taken Math 30. Teague, have you completed Math 30? Yeah. And Sasha, I don't think there's anybody else. It's more a Math 30 question, but it's an interesting question. if you only had 5 energy levels, and that's an impossible situation, but if there are only 5 energy levels, how many different photons can be emitted or absorbed? Does anybody have an idea of how you would go about solving this? We were just talking about permutations and combinations here. Well, each transition would be 1 photon, right? So we could actually trace them out. This would be 1, this would be 1, a second, a third, a fourth. We could go here a 5th, a 6th, a 7th. We could go an 8th, a 9th, or a 10th. There's 10. The answer is 10. Or, and I'm going to write this down in hopes that the Math 30 people remember this, it's 5 choose 2 because there's 5 energy levels to choose from and you need to choose 2. Those of you in Math 30 right now, don't worry about that, but that will ring a bell. When you're in my Math 30 class in the final unit, we'll talk about that. It means you have 5 items and you're choosing 2. And there's a way to calculate it on your calculator. Here is what I want you doing for tomorrow. This is the bottom line when you do energy level calculations. The change in energy of the electron equals the energy of the photon. I want you to do 1 to 3. Now, I don't have answers for question 1. But question 1, you have to fill in all of these. I want to know the wavelength of a photon involved when an electron goes from 2 to 1, and from 3 to 1, and 4 to 1, and 5 to 1, and 6 to 1. I hope you understand the need to use 1242 here. It's going to make your life a little bit brighter. All the way down to 7 to 6. Does your diagram go over to 7 and down to 6? Okay. And then I want you to do 2 and 3 as well. You have to use the energy level diagrams I gave you for hydrogen. You can use either side. I don't care. I also would like you to give some thought when you fill in all of these to which ones are visible, which are infrared, and which are ultraviolet. Which, final comment, that's interesting because at the beginning of the last unit on day 1, we said ultraviolet, visible, and infrared are caused by electrons making transitions in atoms. That's what we're talking about. Why are there only 4 visible? Well, there's a whole boatload of ultraviolet and infrared as well. We just can't see them. But if we put an infrared detector and aim it at the diffraction grating, it starts pinging like crazy. All right, I'll let you get to work. Those 3 problems for tomorrow, please.